Hey, welcome to Classic Momentum Problems. Hopefully you have watched the Momentum Basics video, which kind of describes the important concepts behind doing momentum problems. We just talked about concepts basically. Here is where we start to work on problems with numbers, much like your homework. So, as it says over here, you want to always make sure that you can understand and explain each step of a problem. Because then, if you could explain why you are doing each step, then you get it. So, without further ado, let's get started. Most likely, when doing momentum problems, you are going to be using the conservation of momentum. Momentum is conserved if there is no external force acting on the system. And what conservation of momentum means is that the momentum at the right after the collision is the same as the momentum before the collision. All right, or vice versa. So, and this is of a system, and you might remember from the last video that a system is all the group of objects that are interacting with each other. And so a system can be many different things depending on the problem. Okay, here we have a couple of diagrams, and in these diagrams we could say the system is the two boxes A and B. All right, so we're not going to include the floor that they're on, or we're not going to include anything else. It's just simply the two boxes A and B. In all three cases, A is going to run into B, and so they are going to hit each other. Any internal forces, so there's external means that the force is coming from something that's out of the system. Any force that's within the system, meaning the objects put forces on each other, that's okay. Momentum is still conserved. Now, these are the most basic problems that you could get in one direction. We are going to look at these because I want to show you a really nice way of doing it so that you do not, so that you don't get confused. And you can keep organized and everything else. It's all good. So, you always want to, whenever you're reading a problem, draw a before and an after. So, this side is the before and this side is the after. All right. Now, when we are considering conservation of momentum, the momentum of a system is really, for example here, is the momentum of A plus the momentum of B. So that's the momentum before the collision, and the momentum of A plus the momentum of B after the collision is equal to the momentum before the collision. Now, I always find that it is a really good idea to write out your equation, and then you could put in any of the numbers. All right, so some of you may be used to this and some of you may not be used to it, but we're going to use subscripts with our variables. So we know that momentum equals mass times velocity, right? Okay, so if we are going to find the total momentum initially in our first situation, we would have the mass of A times the velocity of A, so that's the momentum of A, plus the mass of B times the velocity of B. Okay, that is the momentum of B. Now, if we go to the after side, masses are still the same, so it's the mass of A times now the velocity of A, which is different because it hit B. So in a lot of books, hopefully your book says this, we put a little prime here. That's just to mean that it's different, that VA is different than VA prime. VA is the velocity of A before the collision. VA prime is the velocity of A after the collision. And we are going to add the momentum of box B along with it, and we don't want to forget our prime. So really the A So M stands for mass, and A is just a little bling. It's like a little uniform. So the mass of A is M sub A. The velocity of A is V sub A. Don't think that there's any multiplying or anything going on with this. It's, just think, okay, it's uniform, or it's a earring, or it's something that identifies, it's a tag that identifies the object, because both objects have mass, so we have to differentiate between the mass of A and the mass of B. All right, now to finish this up, whenever you're given numbers, it's helpful to get an equation. And so luckily we're using the conservation of momentum, so the momentum before the system is equal to the momentum after the collision. All right, so this is where our equation comes from, and if this were a problem, they would probably tell you what the masses were. If something is at rest, hopefully you realize that the velocity would be 0. And you'd plug your numbers in and solve for the variable that you want. All right, now there's 2 other little tricks that you have to be careful of. All right, so you go about each problem the same way. The initial momentum, and I'm going to just put it up here. The initial momentum equals the final momentum. Your class may use P0 or P0 for initial, same thing. So P initial equals P final, and this is where you're getting your equation from. Okay, so what is the P initial, or what's the initial momentum of the system before? Oh, all right, well, seems to me like we are going to write the same equation. Okay, and over here we are going to end up writing the same equation as well. And because we know that the momentum before the collision of the system is equal to the momentum of the system after the collision, we could put an equal sign here. Now, this is going to give some of you some issues because you are going to forget about it. So we're going to do a problem with a negative in there, but I just want to alert you to that now. You, in these problems, we're using algebra, and you have to pay attention. Just like when we were doing kinematics, you have to pay attention to which direction it's moving. We are always pretty much going to use the number line, and that's positive, and this is negative. So if something is going in this direction to the left, that means that it's going to be negative, and we're going to put a negative value here. This is going to the right, or in the positive direction. We're going to put a positive value here. This is going to the right, so you guessed it, we're going to put a positive value here. And this is at rest, so we're going to make that 0. All right, and then you put in your values and you solve. The very last one, well, coincidentally, take a look here. We have A and B, so here's the momentum of A plus the momentum of B, and you're thinking, man, takes so much time, but no, it's really a good idea to write your equations out using just the variables first. You won't regret it, and you will alleviate a lot of careless mistakes that you might make otherwise. Now, take a look at this. Here, this is MA, VA. Now, just because they're stuck together, that doesn't mean you can't add the momentums of both of them. And don't forget your primes. Come on, computer. There we go. Okay, and we're here for equal. So what's going to be the difference of this? Well, all right, let's do some... Oops, wrong way here. All right, let's look at this a little bit closer. All right, through the magic of electronics, we've all of a sudden have more room here. So now let's see. You're going to find that you might have a problem solving for all the variables because you're only going to be given, so we have a lot of variables and we don't have enough equations. But in an inelastic collision here, these two are stuck together. And what does that mean you know about VA prime and VB prime? Well, if they're stuck together, they're going at the same velocity. So these two variables can really be stated as one variable. So if we were to write this again, equals, you could write MAV prime plus MBV prime. All right, and if you really want to get fancy, you could use the distributive law, because this is probably what you see in your textbooks, just like that. And if you are solving and want to know how fast A and B are moving, you can solve for V prime and life is good. All right. Okay, we're now going to do 3 one-dimensional momentum problems where each of them has just a little bit of a twist that might stump you. So we want to make sure that you're not stumped. So let's go back to this. Oh, computer, work with me here. All right, we're going to try this again. Try this one more time, and let's do black. Okay, we have, oh good, this works. Okay, so we have A and B, and B is at rest, just like before, and this is A, and this is B, and it turns out that A hits B and it actually bumps off and goes the other direction. We ultimately want to solve for VB prime. All right. Now we are given the fact that the mass of A is 1 kilogram. And it is moving 5 meters per second. When we look at this, the B is at rest, so that means that it's moving 0 meters per second. And the problem tells us that B is 5 kilograms. All right. We also know that A is moving at 3 meters per second here afterwards and backwards, and we need to find out the velocity of B after the collision. All right, so we know that the initial momentum of the system equals the final momentum of, oops, screwed up there, equals the final momentum of the system. All right, once again, really not a major pain to do or whatever, and it's totally well worth it. Let's just write out the equation that we're going to use. You are using pen, so it's going to be much, much easier than me with this ridiculous electronic pencil that the internet can't keep up with. So, but I am persevering and trying my best. So the momentum of box A plus the momentum of box B initially is equal to the momentum, please work, the momentum of box A after the collision plus the momentum of box B after the collision. All right, so we put our numbers in. 1, 5 plus 5. Do you see how easy this is and how it helps us ensure that we're not going to make any mistakes. Now, what's the mass of A? Well, it hasn't changed. It's still 1. And the velocity of A, here's where the stumper is. It's going backwards. To the left, it's going to be negative. So we want to put a -3 in there. All right. Plus 5 times VB prime, which is what we're solving for. All right. So this is simply 5 equals -3 plus 5 VB prime. And if we add 3 to both sides, we are going to get 8 equals 5 VB prime. And that, if we divide by 5, we are going to get VB prime of 1 3/5 meters per second, which is 1.6 meters per second. That is the answer. So the trick here is that you always have to pay attention to the direction things are moving. If something is moving to the left, you have to make it negative, or else your answer is going to be wrong. All right. Now, you realize that this is a video, and at any time, if you're confused, you can go and, replay it. Not a bad idea right now is to maybe cover up the answer and do it by yourself. See if you get the same one. Just a suggestion. All right, so let's put this guy up here, and let's do another one. Let's do another one, and we'll make it another color. How about that? Okay, so here, that was an elastic collision, but one was going backwards. So those sometimes are a little tricky. How about if we have, come on, internet. There we go. What if we have an inelastic equation one? These aren't necessarily harder. In fact, some may argue that they're easier, but when you're first doing them, it gets confusing. All right. Please work with me here. There we go. Okay. So this is moving that way. This one's moving this way. This one is at rest. And if you could read that, you are very smart. Okay. So what do? There's no external forces, so initial momentum equals final momentum, and I am going to write my equation. The momentum of A plus the momentum of B equals, before the collision, equals the momentum of A plus the momentum of B after the collision. All right, and so we're going to use the same numbers. This is still 1 kilogram, and this is still 5 kilograms. And now A is moving 5 meters per second, just as it was before, and we want to find out V prime. We want to know how fast A and B are traveling together. And we said what? Because A and B are sticking together, that means their velocity is the same. So this is really MAV prime plus MBV prime. All right, equals MAVA plus MBVB. Okay, so let's just stick the numbers in. Oops, I want to write it nicely right underneath. 1 times 5 plus, this is 0 because B is at rest, equals 1 V prime plus And the mass of B is 5v prime. Oh, so 1v prime plus 5v prime is 6v prime, and this is 5. So we divide, and so v prime is equal to 6 meters per second. And that makes sense because A was moving fast, but it was light, and now they're both moving together, so they would both be moving much more slowly than A. And that is that. All right. We're going to make all of them tiny. We're going to make some room. All right, now the last one is one that doesn't look like the others. All right, so it doesn't look like the others. Let's go magenta here. Okay, so of course I'm going to draw my before and after picture. Now, we're going to draw a picture of a girl, and she's on ice skates, and she is holding a beautiful birthday present. And of course the girl is smiling because she is on a physics video. Let's give her some hair. Okay. Now, the question is if, well, the mass of the girl is 100 kilograms. All right. And the mass of this present here is 1 kilogram. And she throws it. So she throws the present, and the present ends up going 1 meter per second to the right. So, and we want to know how fast she is going to go. There's no friction. And she's on skates, don't forget. So we want to know how fast she is going to go backwards. So we want to find, and we'll call her A, and we'll call the present B. How about that? So we need to find A prime. Okay, well, the hardest part about this problem is the before and after picture. You're like, well, wait a minute. She's just standing there. So if you were to throw the present, what would be the after picture? But if you think about it, this is the before picture. This is the before picture. The after picture is her moving backwards, and the present moving this way. And we said that the present was moving at 1 meter per second. This is actually an inelastic collision, but it's reversed. They start out stuck together, and then they go apart. All right, so, and what is the velocity of both of them initially? Well, they're both at rest. Come on. So annoying. They are both at rest, so that means that their velocity is 0. So what is the momentum of the system, initially? It's 0. So P initial equals P final. So MAVA plus MBVB equals MAVA prime plus MBVB prime. All right, well, this whole thing is 0 because VA and VB are 0. So 0 equals, so the girl was 100 kilograms, and we do not know how fast she's going. And the present is only 1 kilogram, and it is going only 1 meter per second. All right, so we have 0 equals 100 VA prime plus 1. So let's subtract 1 from both sides. And go. Just wanted to give us a little more room. So we get -1 equals 100 VA prime. So divide and divide. And as you would expect, she's not going very fast at all. And we got a negative. What does that negative mean? Oh, the negative means that she's going in that direction, which has to be true, which means that we need that in our answer. Velocity is magnitude and direction. So the velocity is -100 meters per second. All right. So these are 3 problems that if you're going to get stumped, it's going to be something like one of these 3. So hopefully next time you see it, it'll be good. All right, we made it to the end. You thought through all these problems, and really any momentum problem that you're going to get is going to be very much like any of these 3. So I really, really urge you to go back and do these 3 problems again without looking, and make sure you get the correct answer. If you get stuck, go back to the video and listen to the explanation again. In the meantime, I really, really urge you to draw a picture. If you could draw a before and after picture, the better that is. Write your equation. You know that if there's no external forces, then you could write the initial momentum is equal to the final momentum. Add up the momentum of all the objects in your system. All right, and don't forget your signs. If something is going backwards or going to the left, it is negative. All right, that is it for now. And always remember, hardworking scholars can do anything, even physics.